In this video, we'll go through a couple of practice problems from sections 1.1 through 1.4. I'll give the problems in a couple of batches and encourage you to write out your solutions, and then I'll go through the solutions myself. So here is the first set. So for the first part, write out the elements of the following sets by listing their elements between braces. So write these sets by just listing their elements. And for the second set, write the following sets in set builder notation. I'm not going to read them out loud since part of what I'm hoping you will be learning is to read the notation. So I'll just leave it there and I will pause and suggest that you try these out, and then we'll talk about them on the next slide. Okay, so for this is the set 3m minus 1 such that m is an element of the natural numbers. So let's think about some things that are in that set. So m being in the natural numbers means that m could be 1, m can be 2, and m can be 3, and so on. All of the counting numbers starting with 1, or all of the positive integers. So if m is 1, then 3m minus 1 is 3 times 1, 3 minus 1 is 2. If m is 2, then 3m minus 1, 6 minus 1 is 5. If m is 3, 9 minus 1 is 8, and so on. So we're just adding 3 each time to that value, and that goes on forever, and so we can just denote it by the ellipses on the end on the right. And 2 is the first number in that set, so we can end that with that brace in the beginning. So that is the set. This is writing out the set by listing its elements, or the first pattern of its elements in braces. How about the second set, 4 to the x, such that x is an integer? So here, x is an integer, so x can be 1, 2, 3, ... forever. But x can also be 0, it can also be -1, so it's positive and negative whole numbers as well as 0. So those are the values that x can take on. Now what about 4 to the x? So 4 to the 1 is 4, 4 to the 2, 4 squared is 16, 4 cubed is 64, and so on. 4 to the 0, anything to the 0th power we know is 1. 4 to the -1, that's so 4 to the -1. Remember that a negative exponent flips the fraction down, so this is 1/4. 4 to the -2, that would be 1 over 4 squared, so that's 1/16, and so on. Okay, so now we are able to write out the elements of this set between braces as we would write the elements of a set. So this is going to be ... going on forever in both directions. 1 over 64, that's 4 to the -3rd, 1 over 16, 1 over 4, 1, 4, 16, 64, ... forever. So that's writing the elements of that set between braces. Okay, now this is x in the power set of the set containing a, b, c, and d, such that the cardinality of x is equal to 3. So remember, this is power set. That's the set of all possible subsets, such that the cardinality of x is equal to 3. So the things that we are interested in, these elements will themselves be sets because they're elements of the power set, the set of all possible subsets, where the number of elements in the set is 3. So one such possible thing like that, what's a subset of this set that has 3 elements? Well, the set A, B, C is one set that has 3 elements and is a subset of that set up there. Another would be A, B, D. Another would be A, C, D. And I think there's one more, yes. Then there's also just B, C, D. So those are the 3 sets that are elements of the power set of that original set that also have cardinality 3, that have 3 elements. And those are the elements. This should also be between braces. So that is writing out the set by listing its elements. All right. So in the next part, now we want to do the reverse. We want to take this set and write it in set builder notation. So we want to see like what kind of pattern we can observe here. So one thing we could look at is the difference between these, a constant difference. So 6 minus 1, that's 5. 11 minus 6, that's 5 as well. This is also 5, and so on. So it appears that this is probably 5 something. So let's see. We could do 5x, and there's, one option is this is 5 times 1 plus 1. This is 5 times 0 plus 1. So you might do some playing around, but it seems like 5x plus 1, or alternatively 5x minus 4, would both be ways that you could describe each of these values. So this, for example, is 5 times negative 2 plus 1 is equal to negative 9. Okay, so that tells us that if we want to write this in set builder notation, we could write this as 5x plus 1 such that x is an element of, and it's going to be an element of the integers, because it's all positive and negative whole numbers as well as 0. Next, here we've just got negative 2, 1, 0, 1, and 2. So the set before was an infinite set, but this is a finite set. So there are different options. One option is that we could write it, say, as x in the integers, because these are positive and negative whole numbers, such that, let's say, the absolute value of x is less than or equal to 2. That would be one option. Another option could be x in the integers, such that negative 2 is less than or equal to x, which is less than or equal to 2. And there are certainly other possibilities as well. We could get creative. X in the integers, such that maybe absolute value of 2x is less than or equal to 5 would also be correct. It's not the most natural way to write this set, but it's also true. Here's another set of practice problems to try. So for the first two, find the cardinalities of those sets. Remember that these vertical bars denote cardinality. And for the next two, express these sets in interval notation. And what I mean by that is like intervals of the form a comma b, or a comma b, or half open, half closed, or whatever. So pause the video, try those out, and then we'll go through them together. Okay, so if we want to find the cardinality of the power set of the set of real numbers. So this is, note, this set is a set containing just one element. So this is a set containing one element, and the element is the set of real numbers. So that element itself is a set that is an infinite set, but the cardinality of this individual set, note that the cardinality of the set containing the set R is just one. It has one element, and that element is the set of real numbers. Okay, but we weren't asked for exactly that. We were asked for the cardinality of the power set of the set of real numbers. We could answer the problem right away, because we know that if a set A has cardinality n, then the cardinality of the power set of A is 2 to the n. So we could answer our question here and say that the power set of the set containing the set of real numbers would then have cardinality 2 to the 1, which is just 2. So that is the answer to our question. We could also, if we wanted, write out the power set. So the power set of the set containing the set of real numbers is, let's see, what are the subsets of this set? One subset is the empty set, and the other subset is the entire set, the set containing the set of real numbers. And so again, this shows us that the cardinality of this is equal to 2. So this is a bit of a tricky question. You may have instead looked at, and I'll do this in a different color, you might have instead thought about the power set of the real numbers themselves and the cardinality of that. This would be an infinite. The power set of the real numbers themselves would be infinite, because this power set, any subset of real numbers would be contained in this set. So, if the set, let's say the set 0.32, pi, and 5, that would be an element of the power set of the real numbers, the set of all subsets of the real numbers. The closed interval from -16 to 43 would be an element of the power set of the real numbers. It would be a subset of the real numbers. So the power set of the real numbers would be very much infinite, would have many, many possible sets that are subsets of the real numbers. But that is different than the power set of the set containing the real numbers, because, again, this set has only one element, and so there are only two subsets of the set containing the set of real numbers. All right, what's the cardinality of this set? Okay, let's see its elements. This is one element. So the set 1, 3, 5 is an element. The element 2 is an element. The set containing the empty set is an element. And the number 13 is an element. So this has 4 distinct elements. Okay, let's express these sets in interval notation. X in the real numbers such that x is greater than 1. So because it's greater than 1, that means we have an open left side. So 1, and then it's 1 all the way up to, but not technically including, infinity. So this would be the open interval from 1 to infinity. So that's expressing it in interval notation. If we were thinking about drawing it on the real line, it would be at 1 an open circle, and then it would go on and on forever to infinity. So this is the set we're talking about, and this is how we express it in interval notation. All right, x in the real numbers such that -3 is less than or equal to x, which is less than 5. So that's a half open interval. -3 is less than or equal to x, so -3 is included, and that means we use a square brace there, whereas we use an open parenthesis for the right-hand side because 5 is not included. So again, if we were trying to express this on the real number line, this would be from -3 closed circle up to +5 open circle. And it would be all the values in there on the real number line. But again, this is how we express it as interval notation. Here's our last batch of practice problems. And I'd like you to first sketch each of these in the XY plane, and then find the 2 power sets below. So again, pause and try those out. We'll talk about them in a moment. All right, so sketching R cross Z. So we're sketching this on the XY plane. And this means that every time we see notation like this, we always assume that these are on the x-axis and these are on the y-axis. So we could also write this as x comma y, such that x is in the real numbers and y is in the integers. So x can be any real number over the whole real number line, whereas y is just the integers. So y could be 0, that's an integer, y could be 1, y could be 2, y could be 3, 4, etc., -1, -2, -3, etc. And x is across the whole set of real numbers. So this is what our sketch would look like. Just a whole bunch of horizontal lines is what our sketch will look like. And so on forever. Okay, so that's our sketch. For the next one, we want to sketch the closed interval 2, 4 crossed with, or the Cartesian product with the set containing 1, 2, and 3. So here we've got something kind of similar. So our x values can be over the interval from 2 to 4. Our y values are at 1, 2, and 3. So our just really basic sketch here would be a bunch of horizontal line segments. And this would be our set as a sketch. All right, let's find the power set of the set containing x as well as the set 1, 5. So the power set is all subsets of this set. So let's see, it's a set of subsets. So the empty set is a subset of any subset. Another subset would be the set containing just x. Another subset would be the set containing the set 1 and 5. And the last subset would be the entire set itself, the set containing x, as well as the subset 1, 5. So that would be, and we need one more brace to end that. So the power set is the set of all subsets. So that is the power set of that set above. Note that the 1 and 5 can't come apart, so we don't have just 1 by itself or just 5 by itself, because the set 1, 5 is an element of the original set. All right, how about the power set of the Cartesian product of the set 1, 4 with the set just containing A? If we want, we could do this in 2 steps. So we could first find the Cartesian product first. So this is the power set of the Cartesian product of those 2 sets. So that's sets, those are ordered pairs where the first element is in the first set and the second element is in the second set. So 1, A would be one element of the Cartesian product, and the other element of the Cartesian product is 4, A. So those are the 2 elements of the Cartesian product. Now we want the power set of that set, so power set of this 2-element set. And so we're going to have, we're going to have the set containing one subset, as usual, is the empty set. Another subset would be the set containing just the element 1, A. Another would be the set containing just the element 4, A. And the last one would be the entire set itself, 1, A, 4, A. And that is the collection of all subsets of this set.